Yes. So, now in this section we are going to look at a simulation, VMDL simulation, which is called hook. I believe I have shown you this earlier in one of the sections, but now we are going to look at it from the perspective of ensemble, that is isobaric, and we are going to have this particular piston which is going to keep the pressure constant around a central pressure point. So, let us first look at some of the parameters here on your screen. And so, now you can see there is number density which is high, it is a solid material at low temperature, and then we also have external pressure of the piston. Let us start with the rigid container. Now, you can see that here and start that. So, you are seeing that rigid container, and let us see no walls. So, it is a periodic boundary condition. Let me create reflecting walls. So, now you can see in this case this particular material is, and now let us focus on pressure, because now we are only looking at pressure. Now, you can see how the pressure is fluctuating sinusoidally around a central part. Now, if you look at, because the reflecting walls, the material has come at the center, because they are reflecting some of the pressure, and this can change. Now, we are going to change some of the shape of this system. So, let us become a container with the piston. So, now piston moves it down and you can now see that it has this effect of bouncing, because this is a spring, and we are looking at this sinusoidal curve going up and down here. Nicely done. Now, what we are going to do is we are going to look at this dimension. You now know that this is the length of the piston, or which is the current position of the piston. Now, if we put more pressure, so let us stop it and then increase the pressure. We are keeping the mass same, and then we move forward. So, now you can see that more pressure is given and the vibrations are damping because of the external pressure. So, this is a isobaric situation here, because you are essentially putting the pressure, so that fluctuates, but then it at certain point it will go to equilibrium pressure. And so, this is situation. And now, if you want to find the Hooke's law, which essentially says that there is an elastic limit, stress and strain are related linearly up to a certain limit, which is called elastic limit. So, if I increase the strain, increase the stress, so if I pressurize it, then there will be increase in the strain. So, we are essentially changing the configuration of the cell. So, whether it is compression, in this case compression, or expansion, you will see the changes in the length, bond length, based on some of these compression effects. So, now let us do that. We pause it. We again increase the pressure. Let me also increase the mass a little bit, so it becomes thicker piston. So, now you can see that again it is because we are now pressurizing it and going to the bond lengths which are very close to each other, you will start seeing the effect of repulsion as well, but it is now has pushed it down to a certain level. We can also look at the extreme situation, but if you look at here, the pressure is now becoming constant around 2.0, which is showing that it is coming down to an equilibrium pressure point. Now, let me stop it, and then we are going to go to extreme pressures and no mass change. So, I am going to go high pressure here, move that. So, now you can see that because of the spring system, the spring is now moved down further, and this is the fluctuation initially, but as you let it run, you will see those fluctuations eventually will subside down to the smaller scale, and that's and this is a very sinusoidal behavior that you are looking at. F is equal to m a, and now you are looking at the spring. So, in this case, force is equal to minus k x. X is the displacement delta x, and the k is the spring constant, which is connecting all these particles through a spring. So, that is the overall spring constant around all the system. Now, you can see the amplitude has gone down. So, fluctuation is subsiding. However, there is still fluctuation, and as we look at here, we are let us look at the real units, and if you focus on the pressure, it is 8.4 Pascal is going up, to 8.65 and it's coming down to 8.70. So, around 8.7 9.10 we are looking at that pressure is there. Now, in this case, because it is also temperature constant, we have seen this temperature as being constant. So, if I now use the TPN ensemble, temperature and pressure constant, we are now going to increase the temperature. So, now it should lift that because of the additional kinetic energy, springs are going to expand and they will lift the piston up. You can see that effect right away is now lifting up the piston, and if you look at the, because of the temperatures is also breakage of some of the springs. So, it is almost becoming gas like, but pushing pressure up. So, this is constant pressure. Again, if you look at the pressure versus time, it is fluctuating but constant. Now, if you look at the temperature versus time, that is a constant parameter here, and is changing, fluctuating a little bit because of the pressure changes, as both are constant and volume is constant. So, now we have TVN ensemble, and that we have been able to do by using some of the methods which were devised by Parnello Rahman and Anderson, which are the neat techniques to change the dynamics of the particles in a way that you can use resistance term, or you can use Nose-Hoover thermostat, and also Parnello Rahman condition for constant pressure. With this two, we now have a system which is what we call TPN, temperature, pressure and number of atoms constant. Thank you. So, now let me revise very quickly what we have learned so far. Number one, we understood that property calculation we can do from thermodynamic all the way to some of the dynamic property, thermodynamic like temperature, pressure, etc. to we can look at some of the properties. Those are structural, which is G of R, which gives us understanding about the structure of the material. So, we are looking at crystalline structure have certain number of neighbors. So, this is where we look at the first neighbor, second neighbor, third neighbor. This is where we can find out what crystal structure it exists utilizing radial distribution function. Then we also looked at some dynamic properties like mean square displacement. So, we look at the delta x displacement of a particle from its original position, and if it becomes linearly increasing, then it is a liquid, and or if it is becomes a constant value after certain mobility, then we call that as a crystalline structure. So, there are various parameters that we are looking, one from the structural perspective, another in dynamic perspective. Most important thing we also learned in this these sections is that there is a velocity autocorrelation function. The reason I am emphasizing, because that is the starting of the transport coefficient or linear response theory. And so, if you look at some of this correlation function in the system which are hydrodynamic system, or even the velocity autocorrelation function, we have a nice way of looking at velocity autocorrelation function and looking at the particle with itself correlating from its initial velocity. And if you look at that, we can go through all three phases, and we saw in velocity autocorrelation function that if it is a gas phase, then it if you look at the change in the velocity autocorrelation over time, it is really a nice exponential decay. If you look at and it remains above the positive value, it goes to 0, decaying in exponential way. If you look at the liquid phase, then there is exponential decay going to the negative value and then becoming asymptotic to the 0 value. But if you look at the solid, then it goes to it is exponential decay, but it is also fluctuating just like a damped vibration. Finally, if you look at the vibrational frequency, they are coming out of the Fourier transform of the velocity autocorrelation function. That gives us a very good power spectra which connects with the generalized vibrational spectrum. So, we have really now understood lots of properties, and we will continue to look at some of the other properties which we will call transport properties. Thank you.